In the last video, I talked about qubits, and I said that qubits were two-level quantum systems. So we would represent a qubit using this ket notation, which I also introduced in the last video. And given that this qubit is a two-level system, we have two probability amplitudes associated to this qubit. And I mentioned something called Born's rule, which is how these probability amplitudes actually relate to measuring your qubit in either state. Because remember, each of these components corresponds to a state that you could observe your qubit to be in. And Born's rule essentially says that the probability of measuring, we'll call it state alpha for the first state, is equal to the magnitude of alpha squared. And we have to take the magnitude first because this is a complex number. So this gives you the representation of the actual probability of measuring your particle there. And of course, if these are probabilities and our qubit can only be in one of two states, we have the relation that one should be equal to the magnitude of alpha squared plus the magnitude of beta squared. And just real quick, I also talked about this bra notation, which is the conjugate transpose of the ket. So you just transpose your vector and you take the complex conjugate of both of its elements. And I said that since we're working with vectors, and this is our basic unit of information, it's natural that our quantum logic gates will be linear transformations, and specifically they have to be unitary. In this video I want to go over what it means to be unitary and why we need to enforce this requirement in the first place. So really quick, a unitary matrix, we'll call it U, is one that satisfies the following. U times U dagger, and I'll talk about what U dagger is equal to the identity, which is also equal to U dagger times U. And this dagger is essentially the way we took the conjugate transpose of our vector. This is the analog of that, but for matrices. So you transpose your matrix, and then you take the complex conjugate of all of its elements. So let's just see what that looks like. Say we have some unitary, A, B, C, D. Then U dagger, our rows become columns and the columns become the rows. So we have AC, BD, but we also take the complex conjugate of every element. So what this says intuitively is that any transformation we're going to apply onto our qubits has to be reversible, and also has to do something called preserving the norm. And the norm of a quantum state is this thing right here. It's taking the magnitude squared of all the elements and summing them. So it makes sense that our unitary transformation would need to preserve this norm because we still want our probability amplitudes to be correlated to actual probabilities. So we want them to add up to 1, regardless of what transformation we make on those qubits. So this checks out. But why do we need our transformation to be reversible? And this was something that puzzled me a lot in the beginning when I was learning about quantum computing. And I think the best way to understand this is to first ingrain in your head the idea that information is physical. So information is physical. And it's hard to wrap your head around this at first because you think of bits and you think of qubits as these sort of abstract objects that don't actually have any physical, tangible thing related to them, but in fact they are. They are physical things and they interact with the environment. And this is something that becomes abundantly clear when you're working in quantum computing. So we can no longer disregard this fact. In classical computing, it's okay to think of your logical bits as something that only exists on paper, but with quantum computing, the actual physical device we're working with is a lot more delicate than that, and we have to be careful of when our qubits actually interact with the environment. So essentially, the reason why we require this reversibility is because physics is reversible. The laws of classical physics and the laws of quantum physics are both set up in a way where it's reversible. So if we have the complete knowledge of a state at one point in time, we should be able to reverse the clock and figure out where that state came from and also how that state is going to evolve in time. And if you are working with quantum gates that are not reversible, what that essentially means is that you've given up some information to the environment. So if you have some state Q, and this evolves to Q prime, but you don't have a way to get back, which means you don't have enough information here to decipher where you came from. This means that given that physics is reversible, what actually happened was you did apply unitary transformation to this, but you just don't have all the information here. You gave up some information to the environment, and because of something called quantum entanglement, this is going to cause problems for us in our computation. So we want to avoid that at all cost. And this might seem confusing at first, but I'll get into this in later videos. Qubits essentially can become entangled. And if you're entangling your qubits with the environment, you're introducing unwanted correlations that are going to interfere with your actual computation. And this is the reason we require reversibility. So we're just going to accept that for now. Every matrix, every transformation is going to be a unitary. In fact, there's one thing that we can do to our qubits that's not a unitary transformation, and that is measurement. So measuring a quantum system essentially collapses the whole state to just one of your potential states that your qubit could be in. And this is a nonlinear transformation, and it's the only one that we're allowed to make in quantum computing. And we want to make sure that we do all our necessary calculations and computations before we make a measurement, because measurement in general is going to disrupt our state in a way that's not reversible. So we want to make sure we're going to read out some information that will be useful to us by the time we're making that measurement. Okay, so now that we've gotten this out of the way, we have unitary operations that we can do to our qubits, and then at the end of all that we can make a measurement which is nonlinear and non-unitary. So what are some unitary gates that we can make? Well, let's consider a qubit that starts out in the computational basis state 0. And remember, this is just a vector, 1 and 0. I'm just going to give you guys a unitary matrix right now, and let's see how it acts on this. So this is a matrix called a Hadamard, and it's a very important matrix it's a very important transformation that you tend to use a lot in quantum circuits. In fact, most quantum circuits begin with Hadamards, and the reason why it's important is because it puts your state into an equal superposition. So the actual matrix looks like this. It has this normalization factor here, and then it's 1, 1, 1, -1. So let's see how this puts our qubit into a superposition. And I'm just going to call this H now. So if we apply H to our qubit, we have the following. And now we can just carry out our normal matrix multiplication, which will give us 1 plus 0, 1 plus 0. And this is an equally weighted superposition of both of our up and down 1 and 0 states. So now I can write this in Kettenbrough notation as 1 over the square root of 2, 0, plus 1. And now you can see why this might be useful to us, having this Hadamard, because we can take our 0 and put it into 0 plus 1. That's good. Now let's see how this acts on, what if we started in the state 1? Well, then we would have 1 over the square root of 2, 1, 1, 1, negative 1, and then 0, 1. And we can do the matrix multiplication here. It's going to give us 1, and then negative 1. So we get a different state. It's almost the same thing, but instead of a plus, we have a minus. And this should be a little confusing to you if this is your first time dealing with quantum computing, because it seems like we have, again, an equally weighted superposition. What could this minus possibly be doing that makes it different from this state? Like in terms of what we could actually measure. So if you have one state, and we're going to call this the minus state, and then the plus state over here is what we had above. What is the difference between these two states? In fact, on their own, it doesn't seem like there's that much difference. So if you want to measure in the normal basis, you're going to get 0 50% of the time, and you're going to get 1 50% of the time. And this happens in both of these. So they seem identical, but they're a little bit different. And we'll get into that in future videos. But I think for now, this is okay. So we've introduced this Hadamard transform. In the next video, I'm going to introduce something called the Oracle model of computation. And this is the standard formalism that quantum computing began with to actually observe what we could compute with quantum computers. And it's very interesting to see the speed-ups we get versus classical computing. So in the next videos, I'm going to introduce a few other unitary transformations along with this model of computation. And we're going to see how this minus sign and this plus sign is going to make a difference throughout our computations. Thank you.